First, we get to the midterm test date based on our syllabus from this. Oh, that's so annoying. Yeah. So let me change a different pen. I have another pen. Yeah, I don't know why. It's not so hard to. Anyway, yeah, all right. Two, same way. Is it because of Saturday, right? All right. So how do I run the total 25 questions? So I split, yeah, because think about 25 questions. If I ask you complete, sitting here in this classroom, 75 minutes, probably too hard, right? Complete 25 questions in 75 minutes. Yeah. So I try to split the load, okay? Yeah. Do not ask you to do too much work when you sit here in 75 minutes. Yeah. Because some of the questions are pretty hard to solve, so you need more time. Okay? So I plan to do in this way. Yeah. All right. So total 25 questions. Okay? I split like this. Yeah. I split in two parts. Okay. First. Yeah. First part, part A, and second part, part B. Yeah. Part A, I do these two type of questions. Okay. Multiple choice, true and false. Only these two types. Okay, part A. Yeah. Part A, 10 questions. Okay, all right, that's part A. Part B, another two types. These two types. Short answers and solutions. Yes, you know, similar to homework. Yeah. Short answer solutions. 15 questions. Yeah, split in this way. Then the time, yeah, I also split time. Okay? Also split time in this way. All right. Part A, 10 questions. I do this way. Yeah. Okay. How do I deliver? I deliver these part A's, 10 questions at a separate time. Okay. So I deliver in this way. Okay. After quiz 2, we will do quiz 3, right? After quiz 2, we will do quiz 3. So I combine this part A with quiz 3. Yeah. Yeah, so I will run quiz 3 soon. Okay? Yeah. All right. Yeah. So for example, this Saturday, I will start quiz 3. Okay? This Saturday. Yeah. Start this Saturday, why I start this Saturday, due 1 week, look at the due date, Saturday, right? Saturday, 1 week. Give you 1 week time to complete quiz 3, but I treat quiz 3 as part A of midterm. Okay? Part A, yeah. When you work on quiz 3, at the same time you work on part A of midterm. So when I calculate your grade, so quiz 3, you still earn quiz 3 grade, right? But I use your quiz 3 grade as your part A of midterm, okay? The first 10 questions of midterm. Yeah. But you have 1 week, you know. So spread the load. So you do not need to spend too much time in 75 minutes on March 13, Wednesday. Yeah. So March 13, Wednesday, you work on these 15 questions. Okay, part B, 15 questions. Yeah. But those 15 questions, so you have short answer and a solution. Yeah, 15. Okay, all right. Then, 15 questions. Yeah. So this part, yeah, let me use the number. Question 1 through question 10. Okay? Yeah. 15, so that's question 11 through question 25. Okay? Yeah. 15 questions. Then, those 15 questions, even those 15 questions, yeah, we know some of the later questions relatively hard, right? Yeah. Early questions, yeah, relatively easier, but later questions relatively hard. Yeah. So I like to do in this way. Okay, all right. All right. So I split again, yeah. Question 11 through 20, yeah. Must be done in class, okay? Yeah, yeah, yeah. The last five questions, 21 through 25, second chance at home. And due Saturday. Okay? All right. Due Saturday. Yeah. Because March 16th, Saturday, that's the deadline. Okay? Yeah. So when you go home, I post the last 5 questions from 21st through 25th. Okay? Yeah. So in class, you should spend your time more on question 11 through question 20, okay? Because you only have one chance to do, okay? But the last 5 questions, relatively more challenging, so you have second chance. You can work at home, okay? Yeah. So that's our midterm arrangement. Okay? Yeah. Yeah. Hopefully in this way, you have plenty of time to work on all these 25 questions. Yeah. Yeah. So that's the plan. Yeah. Any question? Yeah. That's the question.
Questions on the midterm.
Yeah.
So I know, like, you have the study questions that you'll release on Canvas, and you'll say, like, hey, this is one that's going to be on quiz, this is one that's going to be on the homework assignments. Are the questions on the midterm then going to be from those, or are they totally separate from those questions?
Those, yeah, I derived from those old questions. Yeah, So I modified, using my creative way to modify. Okay. Yeah, but the content, style, materials, all same. Yeah, yeah, all same. Yeah, yeah, yeah. So, yeah, same materials. Yeah, but there are so many different ways I can ask you questions, right? Still, you could have some challenging questions. Yeah. Yeah. All right. Yeah. So that's about midterm. Yeah. Hope, it looks a little complicated here, but hope no confusion for you. Yeah. So it's clear. Yeah. I mean, just this Saturday, you will see quiz number 3. Yeah. But I will write it, quiz number 3, but that part equals part A of midterm. I put in a title, okay? Quiz 3 equals part A of midterm. So you will see it, okay? So get you, make sure you treat it seriously, okay? Yeah. That's the part A of midterm. Yeah. Yeah. All right. So then, remaining 15 questions. Yeah. In class, I give you all 15 questions. Yeah, because some students, they can solve all 15 questions. Okay? But you just know, on the test paper, I write instructions. The last 5 questions will also be posted in Canvas, so you have a second chance to complete it by the deadline, March 16th, Saturday. Okay? I put that instructions in the test paper, so you won't miss that. Okay? So when you read the instructions, so you will see the requirement. Yeah. Yeah. So if you do not feel hard, then you just solve all the 15 questions. But in case, so I expect most of you may need a second chance for last 15 questions. Yeah. So you can use your time efficiently in class. Okay? Yeah. All right. Yeah. So that's the plan. Yeah. Yeah. So let's do this part 1 review first. Let me go through all 10 questions in quiz 1. Yeah, so if I have more time, I will go back to part D of module 3, so we complete the remaining part. Yeah. Yeah. We may not be able to complete everything, but next class, Wednesday, I will, because I will do review session, Wednesday. Yeah, think about Wednesday. Yeah, Wednesday I want to do another review session. Yeah. Yeah. But your quiz 2, I need to do. Yeah, so here it's pretty hard. Yeah. Wednesday I need to do review session for your homework number 1. I will go through your homework number 1. Yeah. I will do grading, but I may not be able to complete the grading. Yeah. But I will do grading. All right, so for your class, okay. Yeah, your class, you just have 10-something students. Probably I have a chance to complete your grading. Yeah, the other class online, they have 20-something. So I cannot complete their grading. But for your class, 10-something. So I try to complete grading your homework assignment 1, so I can talk about homework 1 Wednesday in class for our second review session. Yeah. All right. Oh, yeah, I also post programming part 1. Yeah, so you can, read instructions. Yeah. All right, so let's. Oh, question. What? 1, 2, 3. First 3 modules. Yeah. 1, 2, 3. Yeah. First 3 modules. Yeah. Yeah. Yeah, I may not, because before the midterm, we do not have much time. After I do the review, I may not have time to start module 4, okay? So before midterm, the time I use for review and talk about project. Yeah, talk about the project, okay? Yeah. So then after midterm, then we can start module 4. Yeah. So, all right. First question here, yeah. So there are 2 ways. The first way, you just apply the formula directly. So we have the formula, but you need to see, we can factor out common factor 2 square out. Inside 2 square, after factorization, 2 square n square, right? Yeah. Because this one, we have the formula. Yeah. Remember the flashcard? I put this formula in a flashcard. That's 1/6n, n plus 1, 2n plus 1. Now you do multiplication by 4, so you get 2/3, the coefficient. 2/3, this one. Okay? Yeah? Yeah. So that's one way, using the formula directly. Yeah. Yeah. In case some students, probably some students, they were not aware of the formula, so they didn't use the formula. Yeah. In that situation, you can plug in numbers. Okay? Yeah. So for example here, this one, when n equals 1, you plug in n equals 1, so you get number. Then plug in 1 in all these 4. Which one is correct? Right? Question. Yeah.
Is that number behind the multiplication sign?
Sorry, which one? What?
Number behind multiplication sign?
Number behind multiplication. Do you mean this behind 1/6? 1/6? Or this one? 6.
The other side,
Oh.
the other side, yes.
This one 4. This one 4. Before, okay. Yeah, this one 4. Sorry. Yeah. It's hard to see. Yeah. 4. Yeah. All right. Yeah, sorry. Yeah. All right. Yeah, because sometimes if you plug in, you may not be able to eliminate 3, right? So then you try, if you cannot eliminate all 3, you try n equals 2. Then compare, so which one gives you the correct one. So that's another way, okay? So even if you do not know the formula, so in the case that the formula is not given, or you do not know the formula, so you can try do experiments using some simple cases. Yeah. First, a few simple cases, and do the eliminations. Yeah. All right. Yeah. Yeah. So that's the usual way you can do. Yeah. All right. Second one. When we evaluate general polynomial, do we have multiple ways to evaluate? Yeah. Yes, we have. Yeah. When you follow this class closely, yeah, for your class, so actually I see the attendance very good. Yeah, so I believe most of you follow the class closely. Okay, so for you it's easy, yeah, because you go through everything. Yeah, but the reason I give you the simple questions, for some students they may not follow the notes closely, especially for those online students. Online students, I look at the video watching rate, so not very good. Okay, just about one half of the students they watch the videos. The other half, so they didn't watch the videos. Okay, so they may not know the simple fact. Okay, they have question based on their intuition. Intuition, they do not know Horner's rule. By intuition, they only know one way to evaluate polynomial. Yeah, so those students, they will pick, evaluate multiple ways. So they say, no, only one way. Yeah. Yeah. So that's for those students, okay? Yeah. All right. Question number 3, since the linear search is too slow, that's true, no, quite slow, okay? It is basically useless to solve any real, it's false. Yeah. The reason also simple, because in some real world situations, we have no better solutions. We have to use linear search. Yeah. That situation occurs frequently in the real world applications. All right. So we cannot say useless. Okay? Yeah. Yeah. So, all right. Yeah. So here. Sometimes useful. Okay? Because we do not have better solutions. Okay? We do not have better solutions. Okay? Yeah. Yeah. For example, I can give you a simple example. Okay? Yeah. In database search, so in the database search, all right, we know original data is stored in hard drive, hard disk. Yeah. When you have a large database, so the original data is stored on hard disk. Okay, all right. So then when you do the search, you query the table stored on hard disk. Okay. Yeah. We know access to hard disk is more expensive, right? Comparing with access data in main memory. Main memory much faster than access on hard disk. Okay, 10 something, more than 10 something times slower. Okay, yeah. So when you do data search when your data is stored on hard disk, you want to reduce the number of visits to hard disk, okay, to make it faster. Yeah. All right. So when you reduce the number of visits, there is a technique, okay, in database search called index files. You use index files to make your hard drive visit as small as possible. Okay, all right. Yeah. So index files, usually you create a special files that sort original database. You sort it because original data usually is not sorted. Won't be sorted. But when you create auxiliary file, we call it index file, they're auxiliary file. You sort the table data. After you sort, you can do binary search. When you apply binary search, you can reduce the number of accesses on hard drive. Okay? Yeah? Because binary search is sorted. Yeah. All right. But the problem is, then after you find your data, you load it into the main memory. Yeah. You load the main memory. Usually you load the whole block of data. One unit, one loading block is one unit, one block. Okay? You load one block of data. One block of data equals 4 KB. 4 kilobytes. 4 kilobytes you load it into main memory. Okay? Yeah. So it contains the data piece you need. This 4K, yeah, because when you load data, you want to load, appropriate data size. Yeah. One page, one block, the whole page, whole block into, yeah. Because in this way, if you need a data in the same block, you don't need to go to hard drive, okay, hard disk. You just use the same block. You can access the same block of data several times. to reduce the hard drive access. All right. But the question is, after you load the whole block into main memory, now here, this whole block, each time, data into main memory. Then you need to find the record, the data record in this block, 4 KB, where is it, right? Inside this 4 KB whole amount of data, you need to find the particular, the record, that part, the data record part, okay? So you do linear search. Okay? Yeah. Because in that block, data is not ordered. Okay? In this block, data not ordered. You cannot use binary search. Okay? Binary search, the data ordered in auxiliary file. Okay? But you load this block, this is not auxiliary file. Okay? This block is contain original data. Original data is not ordered. Okay? So you need, if it's not ordered, you can only do the linear search. Okay? Yeah. So here, how can you say linear search is not useful? Right? That's the only way you can do. Yeah. But it's not too bad. Why we do linear search not too bad? Because 4 KB, it's a small number, right? Small number, when we do linear search, inside main memory, very fast. Yeah. So, yeah, very fast. So here I just want to say, in the real world situations, many times you have to use linear search. Okay? No better solution, so you have to use linear search. Okay? Just some special examples. Yeah. All right. Yeah. So that's question 3. Yeah. Question 4. Yeah. Here we have formula. Yeah. Right? We have formula. Okay? So the formula, you can find it in the notes. 1/2 m plus 1 times p, weighted average for the key that appears inside the array. Then there is another part, the key not in the array, so that's n number of comparisons plus 1 minus p. Yeah. So that's the formula. You need to plug in the numbers. Okay? So 1/2 times 201, n equals 200, times 0.4, 6 or 4. Oh, 6, yeah, sorry, 0.6 plus 200 times 0.4. Okay? Yeah. Answer 140.3. 140.3. Okay? All right. Yeah, but some student, yeah, not you. So I have, I saw this before. Yeah. Some of my old students, they dropped that 0.3. That's wrong. Okay? So I don't know if any of you did this way or not. Because those students, their argument is like this. Here, the unit is number of comparison, right? So they feel unit cannot be fractional number. Yeah, it's true, number of comparisons, you cannot use, fractional numbers, but here we asking for the average number. Average number, then usually you need to use fractional number. When you take average, it's an average. Okay? So if I ask you best case, worst case, then you don't have fractional numbers. So that should be your answer should be integer. Best case, worst case. Okay? But when I ask you average, usually average case, it's not easy to get exact integer numbers. Usually you average out, right? So you're supposed to get non-integer, numbers with fractional part. Okay, yeah. So that's some questions from my old students. Yeah. Just to let you know. Yeah. All right. Number 5, when we apply the linear search, yeah, so the data expect, yeah, the following type, unordered. Yeah. Yeah. Simple. Yeah. Yeah. These questions, simple, ordered, unordered. Yeah. Yeah. Binary search must be ordered. Yeah. So that's very important. Yeah. It happens. Yeah. Sometimes people apply binary search on unordered data, because they forget to check. They forget that condition. Okay. They forget that, the data must be ordered. Forget that condition. They just apply binary search on all the data they have. Yeah. That happens a lot. Yeah. Yeah. Here, yeah. Linear search, yeah. Or unordered. Number 6, we have an optimal algorithm solving this, finding the minimum. Yeah. So we learn that. Simple fact. Yeah. Here you can see some of questions. Very simple. Very simple. Okay? So if you are familiar with our course materials, so easy. Yeah. Yeah. But I still see many students that are not familiar with our class materials. So these simple questions, they couldn't get the points. Yeah. All right. Number 7, when we evaluate a polynomial xn, yes, this question related to our project. So in the current project, the regular part, I do not give you. Yeah, I give you. You need to use repeated squaring to evaluate monomial. Yeah, but I plan to give you an optional part. You can earn extra credit. So that will be based on the background here. Okay, this background. Yeah, yeah. So I haven't posted the optional description. Yeah. So here I just let you know. I will make this background. I will write that optional features you can do. Yeah. Yeah. But I will give you more information. Yeah. Here we have repeated squaring and repeated cubing method. So the question, we say that repeated squaring method can never do worse than repeated cubing. The answer is false. Yeah. Because, yeah, so here. So actually you can answer this question in a simple way. Yeah. Think about when n equals power of 2, obviously repeated. Yeah. So repeated squaring better. Yeah, because power of 2, the structure, you match the structure well, right? But how about when m equals power of 3, now this time, so definitely repeated cubing is better. Okay? Yeah. Repeat cubing is better. Yeah. So one example, 27. You can try 27. 27, if you use repeated squaring, it will be 1 slower than repeated cubing. Yeah, because 27, the structure favors repeated cubing. Okay? Yeah. Not favoring the repeated squaring. Okay? Yeah. Yeah. But for other numbers, sometimes favor repeated squaring, sometimes favor the repeated cubing. Okay? You don't know. Right? Yeah. So that's based on that. Then I create an optional requirement for your project 1. So I ask you to compare repeated squaring, repeated cubing, what time repeated squaring better, what time repeated cubing better, and what time a mixed way of repeated squaring and cubing. Because sometimes we can do partial repeated squaring, partial repeated cubing. We mix them. How about that? That could do better, right? So, but that part, a little challenging. Mixing repeated squaring and cubing, a little challenging. So I give you as the optional requirement. Yeah. Okay, optional requirement. Yeah. Yeah. But I will give you the idea how to do it. Okay. Yeah. In class, I will tell you how to do it. Okay. Yeah. Yeah. Otherwise, it won't be easy. Mixed repeated squaring and cubing. It won't be easy. Yeah. Yeah. The improvement is small. Yeah. Improvement is small, but you have improvement. Yeah. Yeah. So in the real world application, we do not bother because we can choose either repeated square, repeated cube. The difference usually is 1 or 2, right? The difference won't be large, 1 or 2. Okay. Yeah. That's small. So for 1 or 2 save, multiplication save, why we need to, do some extra coding, okay? Very hard coding to get that, right? We don't need. Yeah. Yeah. But here, I like you to do some exercise, practice. So find the minimum number of multiplications. Here, we don't worry about extra coding. We want to practice, right? So we want to practice the coding, okay? Yeah, yeah. Here, the good thing is this method, mixed method. Remember, I talk about dynamic programming idea in Module 3 when I give you a brief introduction. Dynamic programming. So here, I can give you the dynamic programming idea to find a solution. So we can practice dynamic programming. Okay? So for the optional, so this optional feature, I give you 3% extra credit. Okay? Yeah. Quite a lot. 3% overall. All right? Yeah. 3%. Yeah. So total 100, this one optional 3%. Okay? So 3%, so actually we will practice dynamic programming. Algorithm. Yeah. I will give you detail how to do it. Okay? Based on dynamic programming. How to do the details. Okay? Yeah. Yeah, so that's the optional part. Yeah. Yeah. Before the midterm, after we review, we may still have a little more time, so I give you this idea. Okay? Yeah. All right. Yeah. Because today's class, Wednesday's class, and Monday's class, so we have 3 classes before the midterm, right? Yeah. So we can find time to study the. If we cannot find time, then I give you after the midterm. After midterm. Yeah. All right. Yeah. So that's number 7. Number 8. Is it possible that one can find special polynomial with n terms? And here I say n terms. Okay, n terms. No. All right. Yeah. Such that the value of this polynomial can be calculated with less than 1% n of multiplications. Yeah. Answer is yes. Okay? Answer is yes. Yeah. Yeah. You need to use the knowledge we learned. Knowledge we learned. Okay? All right. Yeah. All right. 1 Pascal's triangle, right? Here I didn't mention Pascal's triangle, But you can connect to that. Okay? Connect to that Pascal's triangle. Okay? Yeah. So what's that? Yeah. So think about when you evaluate polynomial m, not m, okay? Yeah. When you evaluate polynomial, x plus 1 to the nth it's a special, right? Yeah. X to the 1, yeah. So yeah, you can say n minus 1 because n terms, if you want to match that n terms, x plus 1 to the n minus 1 power, that's n terms. Yeah. But one difference is not big, right? One difference is not that big, okay? Yeah. So, yeah. So, all right. So this one, Pascal's triangle, when you evaluate polynomial, use repeated squaring. Yeah, you can use repeated squaring here. So there, the number of multiplication pretty much log base 2 of n, right? Yeah. The number of, when we use repeated squaring, we use log base 2 of n. That many multiplications. Close to that, right? Yeah, close to that. The number of 2, can we control to make it less than 1% of n? When n is large, definitely, yeah, because we know the limit of that log base 2 of n over n, the limit is 0. Close to 0. 0 much smaller than 1%, right? Yeah. So we can control when n is sufficiently large, then log base 2 of n much smaller than 1% of n. Yeah. So with that background, so your answer is yes. Okay? Yeah. If you just answer this question by your intuition, then probably it's most likely it's no. Yeah. How can you use 1% multiplication? Horner's rule allows us to use n multiplications. How can you do that better than Horner's rule? 1%, right? Yeah. Because Horner's rule is for the general. It's for arbitrary polynomial. Here, we only use special polynomial, not arbitrary. Arbitrary, we cannot use 1%, okay? Arbitrary, we cannot use 1%. Still n. Horner's rule is the best for the arbitrary case, general case. Yeah. But here, our Pascal's triangle, the structure very special, so we can take advantage of that structure so we can get a log base 2 of n multiplications. Or close to log base 2 of n multiplications. So we can control it within 1% of n. That idea. So you needed this much background. All the pieces of knowledge we learned in Module 2 to answer this question confidently. Okay? Not guess. Yeah, because if you make a guess, you don't need this much effort, right? Yeah, but if you pay this much effort, then you can answer confidently. Okay? Yeah. All right. Yeah. Hope you can understand easily. Yeah. All right. Number 9, when we talk about the data size concept, we always mean that it refers to number of elements in the array. False. Yeah. Remember, I give you examples. That is not covered by this. This is the most popular case, but we have some, special case. That is the size, the data size can also be interpreted as the magnitude of the data. Magnitude of the data. The meaning is how large is the data, right? Yeah. For example, here we have two examples here. The first example, example 1, prime factorization problem. Prime factorization. Prime factorization, you're only given one number n, you do factorization. One number, okay? But the magnitude is important. How large is that n? That is important. That would make the problem hard. Okay? Yeah. Remember we talk about 1,000-digit number prime factorization. Yeah, we talk about that. That is hard, 1,000-digit. Okay, very slow, extremely slow. Okay, yeah. Only one number, but slow. So the magnitude. So that's our first example. Okay. Second example, remember GCD problem, greatest common divisor. That's also the magnitude. Okay, yeah. Greatest common divisor. GCD problem, yeah. Because we need to calculate only two numbers, okay? M and N. Okay? Yeah. So here the data size equals the maximum of M and N. Okay? The larger one. Right? Yeah. So we can understand the magnitude, the larger one. The value of the larger one we treat as the magnitude here. Yeah. Two examples. Yeah. Yeah. Sorry, I covered the space of our last question here. Given array with n elements, is it possible that one can design algorithms so that can find minimum of this array n minus 2 comparisons? No. Because we know n minus 1 is already optimal. How can you do better than optimal one, right? And nobody can do better than optimal solution, n minus 2. Yeah. So it's simple. Yeah. Simple. Yeah. So for you who are familiar with our course materials, that's simple. Okay? You don't need 1 minute to answer to get a correct answer. Yeah. But, you know, as I know, many students, they're not familiar with the materials. Yeah. Yeah. Especially online students. They're not familiar with our course materials. If they answer the question by intuition, 50% chance they will feel possible. N minus 2. Why not possible? Right? N minus 2. Yeah. Okay? Yeah. Because they don't know N minus 1 is already optimal. They do not know that fact. Okay? Already optimal. Yeah. So by their intuition, N minus 2, yeah, people have a lot of chance to solve the problem by n minus 2 comparisons. Yeah. All right, so that's the review, part A. Okay. Now let me jump to our remaining part of part D. Yeah, remaining slides of part D of module 3. All right. So we are here last time. Remember the verification. Last time we did verification. Verification, there are two parts. Special case verification, we already did it. But this time the general verification. General verification, we need to apply the powerful mathematical tool That's the mathematical induction. Yeah. Here, let me talk about mathematical induction. Yeah. So, yeah, I do not have a lot of time left for the mathematical induction. All right. Yeah. Yeah. So you learned before mathematical induction. Yeah. In discrete math, there is one chapter talking about this one. Yeah. All right. So here, yeah. Yeah. The procedure is very simple. Yeah. But why mathematical induction allows you to verify for all the cases. Yeah. So here, let me delay the answer of this question. Yeah. Yeah. Because at the beginning, you do not have good impression about the mathematical induction. So let's do it first. After we finish the verification, when I do summary, then I answer that question. Okay? When I do a summary, so then I explain why mathematical induction allows us to verify all the cases. Yeah. We do not miss anyone. We cover all the cases. Yeah. All right. All right. Let's run the standard procedure of mathematical induction here. Okay. First step, check the base cases. We did it. The previous topic, we verified. Okay? We did more than necessary. Yeah. The base case, we only need to verify 2, but we did 4. Yeah. Because we want to practice a little more. So we did 4, more than necessary. Yeah. All right. Yeah. Step 2, we need to make induction assumption. We need to assume. Yeah. So based on the result to be proved, we make induction assumption. Yeah. This step important, yeah. But not hard, so not too hard, because it's just assumption, not too hard. You do not need to prove anything. You just make assumption. Yeah. Assume that the formula is true for yeah, so here I use 2, yeah. And we have verified 0 and 1, yeah. So we can include, okay. So actually we can make this 0, okay. 0 less than k less than n, yeah. But 0, 1 verified. We know it must be true, okay. Yeah. All right. So yeah, for n greater or equal to 1. Okay? The smallest n is 1. Yeah, but usually it should be greater than that. Okay? Greater or equal to 1. Yeah. So here we carefully, this is the range. In the induction assumption, range is important. Range important. Yeah. Okay? All right. Yeah. Yeah. All right, so that's our induction assumption. Step 2. Step 3, the most important step, the critical step in mathematical induction, the hardest one. Yeah. So that is, yeah. All right. Yeah, so I need to complete. Yeah. So here, this range thing, yeah. But I need to complete. In this range, the Fibonacci, this formula is correct. Okay? That's assumption. Okay? Assumption. Yeah. You may ask me, how can you make that assumption, right? How can you make that assumption? Yeah. So, in the summary, I will answer. Yeah. In the summary, yeah, I try to answer. In the summary, when we look at the whole picture, yeah, I will answer that. Here, we just do it. Do like this. Yeah. All right. So the last step, the critical step, yeah. Step 3, verify that f sub n plus 1 equals, we use the same formula, but we apply it for k equals n minus 1. K equals n minus, plus 1. Yeah. For k equals n plus 1, this time we need to prove it is true. Verify it is true. Yeah. We cannot assume it is true. We have to rigorously prove it is true. Okay? Yeah, here. Rigorously prove that it is true. That's important. If we can do that, then we have the whole rigorous proof. The whole proof is rigorous. Okay? Yeah. So we're done. Yeah. All right. So that's the idea. Next, I show you how to prove. Okay. All right. We need to do formula transformation. Yeah. In the proof, we need to manipulate the formulas. So we do formula transformation. Okay? How? Yeah, here. Let me show you. Because our goal, now here, this recurrence relation is given, right? It is given. We can always use this recurrence relation. Always correct. So we just apply it. We apply this recurrence relation. It's legal. Yeah. This is a legal step. All right. But when we apply it, can we use our induction assumption formula on f sub n and on f sub n minus 1? Yes, we can. Yeah. Do you know why we can? Do you know why we can? Why it's legal to apply the formulas here? Remember, in our induction assumption, here, let me write here. In our induction assumption, look at the range. What is the range? Induction assumption, range. Yeah, here I use 0 less than equal to k less than equal to n. Okay? All right. Is this n covered in the range? F sub n, is that subscript n covered in that range? It is. Yeah. The last one, last k number, that's n. So if the subscript falls into this range, you can apply this formula. That's the assumption. Okay? All right. The second one, is the subscript n minus 1 falls into that range between 0 and n? Yes. If it falls in the range, we can apply that induction assumption formula another time. How about that? So now you see the range is important, right? Otherwise, you cannot use these formulas. Yeah. So when k is in the range, we can apply the formula. If it's out of the range, we cannot apply formula. Okay? That logic, very simple. Okay. All right. Now, we just work on these formulas, the sum of these two expressions. Yeah. Can we factor that 1 over root 5 out and put the 4 terms inside that big parenthesis? Yeah. When we put here, I change the order, I do the grouping. So here, basically I do the grouping. I group phi to the n and phi to the n minus 1, these two terms, put them together in first group, and last two terms in the second group. Yeah. The reason I group them in this special way, because I put the terms with a similar structure in one group. Yeah, phi to certain exponent. That structure, same structure, I put in one group. Okay, -1 to some number over phi to that number, same structure, I put them in the second group. Okay, because they share same properties. The reason I group them with similar structures because they share same properties. Yeah. All right. After that grouping, let's compare with our goal. Goal, we want to show this formula equals that, right? Yeah. So you compare this expression with our destination expression. Yeah. 1 over root 5, 1 over root 5, the same. We can ignore, right? Yeah. Same constant, multiple. We do not need to consider. Yeah. So we ignore, we can simplify it. We only need to consider the part inside that big parenthesis should be the same. Okay? But inside the big parenthesis, there is this phi, power of phi term. And here, sum of power of phi term. They have the same structure. Can we imagine the terms with same structure should be the same? Yeah. So our first guess, this is our guess. We guess this part should be the same. But we need to prove it. Okay? The second guess, the terms with similar structure like that should also be the same. That's our another guess. So now we only need to show each guess is correct. Each guess is correct. Okay? The first one should be easy because the first one, after simplification, after we do the division by phi to the n minus 1, we just get a phi square equals phi plus 1. Is it true? Phi square equals phi plus 1? Yeah, because this is our second property of golden ratio. Golden ratio have two properties. First property, 1 equals phi square minus phi. Second property, phi square equals phi plus 1. So this is our second property. So it's correct. Okay. If it is correct, then we multiply both sides by phi to the n minus 1. So we get our first guess, right? That's our first guess. So we verified. It's correct. Okay, the first guess. Yeah. All right, now let's work on our second guess. Yeah. Second guess, a little complicated. Yeah. Yeah. So this time, so this is our goal. Our goal, yeah, this is our, new goal. We want to prove this equality. Okay? Yeah. Here we use backward thinking. In order to show this is correct, so we do deduction, backward deduction. Yeah. All right, backward thinking in this way. Yeah. Can we eliminate the denominators by multiply common denominator? Yeah. So this is common denominator. Common denominator. So we multiply both sides of the equality by that common denominator, so we get this equality. Okay? This equality. But -1 to still, still block our view. Okay? So we cannot see things clearly. Okay? So it blocks our view. So we want to simplify it. -1 certain power, we want to simplify that. Okay? Yeah. To do that, we multiply -1 to n minus 1 both sides. Both sides, left hand side, -1 to 2n, even number of power, that number is 1. The right hand side, odd, it's minus, even, plus, so 1 equals n squared minus phi squared minus phi. That is our first property of golden ratio. First property of golden ratio. It's correct. Okay? So first property. If it's correct, because we do backward thinking, backward deduction, now we going forward. Yeah. The last step is correct. We can go forward because two directions. Okay? Either way, we can go. Okay? Two-way deductions. Okay? So we can go backward, we can go forward. Now, since this last step correct, now we do forward deduction. Yeah. So we can get the very first step. Yeah. So that's this step. Okay? So our second guess also correct. Yeah. Our two guesses both correct. So the whole step, yeah, verified. Yeah, verified. The whole thing correct. Okay? Whole thing correct. Yeah. All right. Yeah. Okay? Yeah, just 2 minutes. Yeah. 2 minutes. Yeah. So here, that's the way we apply mathematical induction. Yeah. All right. So here, those 2 minutes. Let me explain why this step number 3 allows you to cover all k numbers. Yeah. All k numbers. Yeah. All right. After step 3, we show n plus 1. When k equals n plus 1, it's also correct. Yeah. Then, can we expand our range to n plus 1? Yeah, because our range before step 3 only cover 0 up to n. But after step 3, we expand it to cover up to n plus 1. All right? Yeah. After we expand to n plus 1, can we expand it to n plus 2? After we expand to n plus 2, can we expand to n plus 3? Yeah, because the step 3 always allows you to expand one more, right? So every time we expand one more, until we cover all the positive integers. How about that? So eventually, this formula will be true for all positive integer subscript. Yeah, that's what we need. So that's the power of mathematical induction. Okay? You only need to prove step 3, then you cover all integers. Yeah. All right, so that's it.